Hi everyone, my name is Joël and I'll present our work called GeoSANE, Learning Geospatial Representations from Models, Not Data. This is a joint work with Damien Falk, Stella Yu and Damien Bort from the University of St. Gallen, the University of Michigan and UC Berkeley, and the ESA Phi Lab. So for a bit of a context here, remote sensing foundation models have become very successful in the past few years. And this is true across many geospatial tasks and many modalities. But the thing is, each model is usually trained on different data sets, different sensors, different objectives, meaning that their knowledge remained quite fragmented in this whole ecosystem of available models. And today, if we want, for example, to solve a new task, we typically have to choose one specific foundation model over another and then fine-tune it. But which one to choose and based on what, this still remains a valid question. Now, in this work, what we propose to do is to take a different perspective on this question. So instead of learning from satellite imagery directly, we propose to learn from the models themselves, from all those available models, and more specifically from their weights. So our idea is to learn a shared latent representation of remote sensing foundation models or remote sensing models in general, and use it to generate new models on demand for downstream geospatial tasks. And this is what we call here GeoSANE. Now, GeoSANE works in 3 stages. The first stage is to collect a large and heterogeneous set of remote sensing models. We do this by using Hugging Face. So all the models we collected include CNNs, transformers, could be for segmentation, classification, multimodal models, so a very heterogeneous set of models from Hugging Face. The second step is to tokenize the model weights into sequences of weight tokens and then train a transformer-based weight-based autoencoder to learn a shared latent representation of these models. And finally, given a prompt architecture, so for example, a VIT or a SWAN or a ResNet, so we give a prompt architecture and then we can sample from this latent space and generate new model weights that are ready for fine-tuning that would be used in this architecture. Now, the question is, how does this space look like, right? How does the shared data space would be interesting to understand how is it structured. And here we visualize it using UMAP projections of the token embeddings. On the left, the embeddings are colored by architecture type, and on the right, it's the same latent space, but it's colored by sensing modalities. And we can see that GeoSANE learns somehow meaningful structure in weight space, and GeoSANE also captures relationships between different model families. Also, the models that are using similar modalities tend to cluster also together, even across different architecture. So this is interesting, and it actually tells us that GeoSANE captures both architectural and modality-specific information within a unified representation space. Now, once the latent space is learned, the use case is that GeoSANE can generate models of different sizes and different architectures on demand. And here we show generated classification models ranging from very lightweight mobile nets to large vision transformers, also ResNet, so you can generate anything as long as you have the right model prompt. Also, GeoSANE is not limited to classification. You can also generate segmentation models, the UNets, SWAN-based architecture, same for object detection tasks, where we generate ResNets, SWANs, VITs, etc. Next, we compare the GeoSANE. I think this is very important. We compare GeoSANE generated model against existing remote sensing foundation models such as SetMAE, ScaleMAE, Chroma, DOFA, etc. So the setup here is that we generated models using GeoSANE. This is the last row of the table, and we evaluate this model across 10, those models across 10 benchmarks, and we compare them with available remote sensing foundation models. And we can see that GeoSANE achieves the best or the second best results in most cases. And what is important to keep in mind is that these models that are like this last row, the models generated by GeoSANE, are not pre-trained from raw satellite imagery, right? But they're instead just generated directly from the learned weight space representation. So that was a very brief overview of what GeoSANE is. Just the main takeaways that you have to keep in mind is that GeoSANE learns geospatial representations directly from model weights instead of data. GeoSANE generates competitive models on demand for classification, segmentation, and detection across multiple modalities, multiple architectures. And finally, the models that are generated by GeoSANE consistently outperform training from scratch and match or surpass even state-of-the-art remote sensing foundation models. So that was it. Thank you for listening. If you're interested, the code is available on Git. You can also read the paper, and if you have any question and you want to reach out, you can also use the email address here. Thank you.